Okay, now we'll start lecture 11. This is a new hardware chapter, chapter 2. We will talk about the memory interface. How do we interface memory to the processor? And by the end of the chapter, we should know comprehensively how to deal with memory devices, different categories, ROM, E squared Prom, static RAM, and dynamic RAM. And we'll know the necessity of decoding an address, what addressing decoding means, and we'll see how to interface memory to the 8088 processor as well as to the 8086 processor. Okay, we looked at this pin configuration in the previous lecture, and we should now comprehend what the function of each of these pins is. Okay, every microprocessor based system should have some memory because unlike the microcontrollers where the memory is built in inside the chip of a microcontroller, microprocessor has to be interfaced with external memory devices. Okay, so two types of memory are addressed. Two main categories: read only memory, a memory you can read the data from, you cannot write into this memory, and the beauty of this memory is it does not lose the data when the power is off. When you turn off the power of a ROM, data is returned. You can get the data back. So you don't have to always supply power to the ROM. Unlike the ROM, the RAM, random access memory, it's again a type of memory, different from ROM. So you can read and write. You can read data into the RAM and write a data from a RAM, but you have to pay attention that data is being accessed as long as the power supply is on. When you turn off the power from the RAM, you lose the data inside the RAM. So if you like to keep the data you're dealing with through RAMs, you have to store it somewhere else. Alright, this is a typical memory device. So a memory device has address connections from A0 to AN, so N plus 1 pins to provide the address, and output pins O0 through ON pins to get the output from. And this is a memory device chip, so you have to select first this chip by providing a low signal to this pin, chip selected. If this type of memory is a memory you can read from and write into, you have to decide, are you reading a memory location from this device? If you are doing this, you have to supply a low signal to your output enable. You have to enable your output. And if you are writing, you have to supply a low signal to this pin, indicating that you are providing data to this memory device or you are writing data to this memory device. All right. Memory pin connections and the address connection. As we previously indicated, memory devices have address pins. You use these address pins to select a specific memory location within the memory device. and the address pins are labeled A0 through AN, where N plus 1 is the total number of address pins. For example, for a memory of 2K, meaning 2K bytes, this memory device has to have 11 address pins to cover all 2K memory locations. And they should be labeled A0 through A10. Okay. And if we start at an address of this value, 10,000 hexadecimally, 20 bits coming out of your microprocessor, and this is the starting address to communicate with this memory device. Your ending address should be the 2K minus 1, which is this value. So your memory starts at this address and ends at this address. Okay. So this is regarding the address connections. How are the data connections? As we previously indicated, each and every memory device should have data outputs or data inputs, data connections. These connections are used to read the data from a memory and write a data to memory if the memory can be written into as well as read from. Okay, data pins are labeled D0 to D7 in most of memory devices, because as we mentioned it many times, memory is byte addressable. So you have to provide an address for each and every byte. So this is D0 to D7 is a byte of memory. It has to have some address to get these D0 through D7 out of the memory, or to write a byte inside your memory from D0 to D7, which again indicating that memory is byte addressable. Okay. There is something called memory organization. By memory organization, we mean the memory. How many different memory locations does it have, and how many bits it contains in each location? For example, 1K by 8, indicating that this specific memory device, the memory is organized as such. You have 1K memory locations, each of 8 bits, while these 16K by 1 indicates you have a 16K memory locations, each of a single bit. So each memory location contains only a single bit, and sometimes we need such a memory if we are producing some single bits like the parity bit. In some other incidents, you may require a memory location of 4 bits. So this is now a memory device containing 64K memory locations, each of 4 bits. Such indications are referred to by memory organization. while the capacity is the total number of bits. For example, this memory has a total number of bits equal to 1k times 8, which is 8k bits, while this one, this memory organized as such, contains a total number of bits equal to 16k times 1, which means 16k bits, while this third one contains a total number of bits equal to 4 by 64, which is 256k bits. Okay, the third connections, we discussed address connections, data connections, and now the selection connections. So each memory device has to have some connections for it to be selected to enable it. So they can be, these are the selection connection. A pin through which you select the chip, we call it chip select. Sometimes they call it CS, sometimes they call it CE for chip enable, or simply select. So the memory has to have such a pin to be selected from or activated through. You activate the memory through CS bar or CE bar or S. Alright. And they have to be active, which means you have to provide a zero logic to any one of these pins. And if you provide a 1, this means you're not going to communicate with this specific memory chip, because in most of the cases you connect more than a memory chip to your microprocessor, and this chip select connection enables you to communicate with the microprocessor through a chip at a time by selecting this specific chip. All right. And then the fourth type of connections to the memory is the control connections. So we discussed address connections, data connections, chip select connections, and now the control connections. These are connections which inform the memory whether a data is to be taken outside or brought into the memory. So in Rom devices, we have a single control pin because we can only read. So you enable your output or you're gating your memory. Some manufacturer label this pin as OE, output enable, or just gating. You open the gate of the memory to get a data from. And this is the only control pin provided through ROMs. All right. But if both output enabled and the chip enabled are active, so you can communicate through this ROM chip and getting a data from. Both have to be active, the output enabled pin and the chip select or chip enabled pin. If the output enable is not active, you cannot get data from your memory chip. Unlike ROMs, RAM devices are devices that can be written into and read from. So they have to have two control inputs to decide whether you are reading from the RAM or writing into the RAM. Sometimes they multiplex it into a single pin labeled R/W bar. You provide a 1 if you are reading, you provide a 0 if you are writing. Okay, and sometimes they use two control pins, W bar for writing, OE or G for reading. You enable the output to get the output from your RAM or you're writing to your ROM. Okay, let's now pay attention, get a little closer to ROM memory devices. ROMs are devices which stores data permanently, like your system software. Your system is configured and defined by some software which should be unchanged whenever you boot the system. You run this software, so this software has to be stored in a read-only memory because it is kept inside the memory even if you turn off the power from your device. Whenever you provide power to your device, the ROM will run this software to configure the system and use your system the way you used to operate it. And it is also called non-volatile memory. Again, the term non-volatile memory indicates that the data is retained inside your memory. It doesn't go away. And these devices is available in forms of Prom, programmable ROM devices that can be programmed. But again, you can, after being programmed, you can only read the data from, and you don't lose your data if you turn off the power. And EEPROM, Erasable Prom, programmable read-only memory. This is a modified type of ROMs where you can erase the program and reprogram it. But again, once programmed, your data will be retained inside this memory and you don't lose it if you turn your power off. Okay, and this kind of ROM, EEPROM, they used to shine ultraviolet for 20 minutes to erase the data inside the Prom and reprogram it, which requires a setup for a UV ultraviolet source, concentrate the light and let the light go through a glass window inside your memory device to erase the data. And this was not easy to deal with. This is why they modified a bit by the E² Prom, or electrically erasable Prom. Again, it's a reprogrammable ROM device where you can erase the written program to your ROM by applying voltage or electric field, electrically erasable. This is easier to erase, easier than providing an ultraviolet source. And a third known type of ROM memory, which is the flash memory. Okay, and we all know this type of memory, but this type of memory can be read fast, but when you write to this flash memory, it's a slower type of device, but it is used, and you can return the data inside this flash memory. If you take the power of the flash, you don't lose your data again. So now let's get a closer to the ROM memory devices. Let's take a look at ROM memory devices, and we'll focus on the EEPROM, whose series number and integrated circuits is 27. Okay, so the EEPROM chips is given the 27 number. For example, here 2704. So this is the series number 27, and this number after 27, which is 04, refers to the number of K bits in your memory device. So your memory device contains 4K bits. How many bytes? If you divide this by 8, you get half K bytes, which is 512 bytes. Again here, this memory chip contains 8K bits. You divide by 8 to get 1K bytes, and so on. Okay, these are the different EEPROM chips of the 27 series. Okay. And each EEPROM chip has address pins, definitely, data pins, and then control pins. And they have two control pins, one for a chip select or a chip enable, and another one for output enable. Okay, we continue with the ROM memory. This is a representative of ROM chips 2716. Again, 16 means 16K bits organized as 2K memory locations, each of a byte. Okay, and here is the chip 2716. So we have 2K memory locations. This requires 11 address pins. 2 to the power 11 is the 2K. So we should have address pins labeled from A0 to A10. Here you are, A0 through A7, 8, 9, and 10. And we have a byte inside each memory location, so the chip should provide us with 8 output pins, O0, O2, and 3, 4, 7. So these are the 8 output pins. So this is the pin configuration of this 2716 ROM chip. Good. Another type of memory chips is the static RAM chip. Static RAM. Okay. The static RAM memory device, as the RAM devices, static or dynamic, they return the data when the power is switched off. And this is why they are called volatile memory. So as long as the power is provided to the chip, you have the data inside. If you turn off the power, you lose the data. This is a type of volatile memory. Okay, they are given the 52 series. And again, this number beside the 52 tells you how many K bits is this chip having, and 256 K bits, if you organize them in a byte-wise manner, there will be 32K memory locations, each of a single byte or 8 bits. So 8 by 32 is 256. And this is how the chip looks like. Again, you have 32K memory locations, which means what? 2 to the power 10 is 1K, 2 to the power 5 is 32, so you should have 15 address pins labeled from A0 to A14. And here you are, A0 through A14. So here are the address pins. Here you don't have 8, 9, 13 and 10. Here is the 10, here is the 13, 8 and 9. And again, each memory location is composed of 8 bits. So this chip should provide you with what? With 8 different output pins. But we call here the pins I/O, because RAM can be read from or written into. I/O 0 through 2, 3, 4, 5, 7. Beside the chip select, this is when you read from the RAM, the output should be enabled, and this is when you write to the RAM, this pin has to be active. Okay, so this is the static RAM chip. Dynamic RAM. So the main difference between static RAM and dynamic RAM, this is dynamic RAM. This is a strange type of memory devices where you have to frequently read and write the data inside your memory locations. Otherwise, you will lose your data even if the power supply is on. So you have to always refresh, we call it refresh your memory. But why do we have to deal with such a memory that needs to be refreshed? Because it's a simple memory. You can pack more number of bits inside the same area, a lot more than your static RAM. So it provides you with a huge density of your bits inside the same area. The capacity is huge as compared to the static RAM. This is why we do use this dynamic RAM somewhere in your system, but you have to design a circuit to refresh your memory, to continuously read and rewrite the memory. Okay, so it returns data only for 2 to 4 milliseconds. So you have each 2 and 4 milliseconds, you have to rewrite your data. Okay, you read it up to 256 times in 2 to 4 milliseconds. You have to refresh your data. Okay, dynamic RAM stores the ones and zeros inside a capacitor. All right, and capacitors are usually leaky electrical elements, so they lose the charge through the connections. So you have to refresh the data when using dynamic RAM, while the static RAM uses transistors to read and write data. Okay, this is again TMS 44 series of dynamic RAMs, and this is a special dynamic RAM where you have 64K memory locations, each of only 4 bits. So this is a special type of memory where you need only 4 bits as your outputs, not a byte in each memory location. All right, this is how this chip looks like. Again, we have 64K memory locations. 64K means what? This is a K, this is 64, so you have to have 16 different pins to address a memory location inside this memory chip. Okay, well, we're getting larger as far as the number of pins is concerned. We're getting larger and larger. This is why they distribute now the memory to columns and rows, and you give an address to access a row and another address to access a column. This is why you need a lesser number of bits. For example, instead of providing 16 bits, you can provide only 8 bits to access a row and 8 bits to access a column. And you switch between accessing a row and accessing a column by 2 signals. Row address strobe, you address a single row, and the column address strobe, correct? So instead of arranging the 64K in a single column or a single row, you arrange them in 8K by 8K rows and columns. So you have to provide only 8 bits for the address A0 through A7, and if A0 through A7 is given a row address, your row address strobe should go low, and then at the next clock edge you provide the 8 address pins to address a column by providing a 0 here at the column address strobe. So we switch between row and column to access a specific 4 bits of data. A specific 4 bits of data you take from DQ1, DQ2, DQ3, and DQ4. So this is where you get your output from. So we reduced the number of address pins by arranging the data into M by N columns. Here 8 columns by 8 rows. M columns by N rows. Here we selected 8 rows and 8 columns, and we activate and we provide the row address strobe by making this pin low, and we switch to columns by making this column address strobe low. Okay, the dynamic RAM, all right, again, when the row address strobe is active, provided by a 0, the first 8 bits are placed on the pins. This will access a row. Okay, this row containing many columns, many RAM cells, each distributed in a column. A single column of these can be read from or written into by activating the other pin, which is column address strobe, to get the next 8 bits and to make you access a column. So this 8 pins of the address is stored in an address latch or a row latch, and this 8 bits of the column is again stored in what's known by a column latch. So the address of the row is latched and the address of the column is latched. So you can now read the cells inside this column, the data inside this column, which has been activated by the column and by the row. So your 16 bits is now distributed between 2 internal latches, each of 8 bits. And the column address strobe pin is used as well for a chip select. Here is a kind of multiplexing your address pins. Okay, if your row address strobe is 0, your A's go to Y, and you would have A0 through A7. This is 8 bits for the first row provided to some chip. If otherwise your RAS bar is 1, your B's go to the Y's. Now B's go to the Y's, which means what? A8 through A15 would be outputted to you through this multiplexer. So in the first, you provide A0 to A7, the first 8 bit, then you provide A8 through A15. So these are two addresses. Maybe you are trying to communicate with two memory chip, two dynamic RAMs. This is the first address of your chip, and this is the address of the second chip. Again, this is a dynamic RAM, a special purpose dynamic RAM, which has 256K memory locations, each of a single bit. Here you are, 256, which means what? 2 to the power 18. So you need 18 address pins. If you choose to split them into 9 by 9 using the row address strobe and the column address strobe, you will have address pins A0 through A8, 9 address pins representing a row. If you provide a 0 to your row address strobe, and representing a column if you provide a 0 to your column address strobe, and you have only a single output pin, because each memory location contains a single bit. So we need only a single output pin, which is D out. Okay, if you are reading from the dynamic RAM and data input pin, if you are writing, you provide the data to be written inside your RAM through this DN. You're getting a data outside the RAM through this D out. Okay, dynamic RAMs are arranged in single inline memory module on modules, one of which is the single inline memory module. And here are two versions, a 30 pin and 72 pin. They can as well be connected from both sides, and we call it dual inline memory module, and they look like this. In this module, connections are made on both sides of the memory card. Right? Good. Now, address decoding. What do we mean by address decoding, and why do we need to decode the address? This is for two main purposes. First, if your microprocessor-based system is to communicate with more than a memory chip, and this is always the case, so we have to provide an address and decode it to know exactly which memory chip we are talking to. Alright? Besides, memory chips provide a fewer number of address pins than the processor can provide. For example, a memory chip may require for 10 address pens, alright, if it's in kbyte range, 1 kbyte range. Your processor provides for each memory location 20 bits. So these 20 bits have to be decoded to produce the required 10 bits of the memory device. So we have to decode the address in order to be able to communicate with more than a memory chip and to talk to memory whose address pens is lower than the processor can provide. Alright, so your microprocessor provides 20 bits for each memory location or for each address. Usually, memory devices have lesser number than this. They provide address pens less than 20. So the solution to this is a decoder. You decode the 20 bits to be compatible with the lower number provided by your memory. For example, if you're talking to a 2K byte chip, which provides only 11 bits, the other 9 bits of your microprocessor have to be decoded. And the simplest ever decoder is the NAND gate. How we do this by an NAND gate, next slide will show you. Here you are. Okay, so we have our microprocessor giving us 20 bits, 11 of which are provided to your memory device, A0 through A10. And the rest of your address is decoded by an AND gate as such. A11 to A19 are all made high. In addition to this control pin, IO/M bar, we're talking to a memory device. So this has to be 0, providing a 1. So you have additional 3 ones here. So all the inputs to your NAND gate are 1s, making this 0, which you use to chip select or to enable this EPROM device. Okay, so this is the way we decode the rest of your address pens, simply by using an AND gate. So the first address is, you have 9 ones, these are 9 ones, and the first 11 bits given to your memory addressing the first memory locations are 11 zeros. So this is your beginning address. Your ending address, your last address in this memory chip is made when these 11 zeros become 11 ones. Okay, so this is your starting address, this is your ending address. So whenever you need to address any memory location inside this chip, this is your range of memory: beginning address, ending address. Okay, we use a decoder which is better than the NAND gate, and we call it a line decoder. This line decoder takes 3 bits as inputs and provides you with 8 different lines, like this one here. Okay, this decoder takes 3 inputs, A, B, C, and makes one and only one of your output lines is 0, under a condition that it has to be enabled. So we have here many input signals, okay, so we can use it to decode the rest of your microprocessor's address pins. This gate number 1 has to be high, gate 2B has to be low, gate 2A has to be low to activate this chip, which is the 3 to 8 line decoder. And this is a truth table to show you how this chip operates. Inputs, alright, and select lines. These are called input lines, and these are select lines. If your gate 2A is high, you provided a high here, so this is disabled now. Regardless of what you provide for G2B or G1, it doesn't care what select lines, they will provide all 8 outputs high. Okay, and your decoder is useless then. Same thing if your G2B is high, regardless of the rest of your inputs or the select lines, your outputs will be all high. Again, if G1 is made low, your device will also be inactive regardless of the rest of your inputs or your select lines, and it will provide you with 8 high outputs at their output lines. Okay, now you are activating your chip, your 3 to 8 line decoder, by providing G2A low, G2B low, and G1 high. If your select inputs are all zeros, your 0 output line would be low while the rest is high. So you can take this 0 output line, you can connect this line to some chip to make it active. It requires a low signal. You take the low signal from this D0, and when you communicate with this chip, make sure to provide this 3 zeros for your select lines. If you have more than memory chip, up to 8 memory chip, you can activate the first memory chip. This is the 0 memory chip, the first memory chip, by providing 001 at the select line, and you take your chip select signal from your first output line of your decoder. If you are communicating with the fifth memory chip, you provide at your input select lines 101, and you connect this chip to your fifth output line, because this line is the older line which is low. And this is how your 3 to 8 line decoder will work, and how you connect it to some microprocessor based systems when you use more than a memory chip connected to your system. Okay, let's talk now about in some more details how we use the line decoder to connect 8 different chips to your microprocessor. So we have this line decoder, 74 LS, low power Schottky, consumes small amount of power, and it is fast because the Schottky technology is used, and it is 3 to 8 decoder, and we are trying to communicate or to interface 8 different chips to your processor, each of 8K bytes. And here you are. So you have from your microprocessor, you're bringing in an address of 20 bits. Each of these chips requires only 13 bits. So we take A0 through A12 from these 20 bits, connect them to your first chip. And to get the data from the beginning address of the first chip, we have first to select this chip. How do we do so? We make A13, A14, A15 all zeros. Okay. If we do this, you have a low signal at the zero output of your decoder. This zero is now provided to this chip select input of the memory, so it makes sure that we are talking to this specific chip, let's say chip number 0. And at the same time, we have to activate this line decoder by providing A17, A18, A19, all ones through this NAND gate. Here you have a 0, so you are activating this G to B. And your A16 should be high. Okay, so your address pins from the microprocessor, which starts at A20 as your most significant bit and ends at A0 as your least significant bit. So A19, A18, A17, and A16 are all made ones and they remain ones. So your most significant hexadecimal digit will always be F. Okay. If now you're talking to the first or the memory chip number 0, you have to provide 3 zeros. 1, 2, 3. Then these are the decoded 7 bits. If you're talking to the first memory location, you have to provide 13 zeros. So 13 zeros. So your beginning address would be F, and you take a 0 from these 13 zeros to make here 0. So F 0, 0, 0, 0 is your beginning address. Your ending address, you provide here 13 ones. Okay, and now for converting them to hexadecimal digits, you have 13 ones. You take a 1 to make the hexadecimal digits here, which would be 1. So F, then 1, and the rest would be 1s. The other 12 would be 1s. So this would be your ending address of the first memory chip, or the 0 memory chip. So if you would like to get connected or to communicate with the next memory chip, you do so, you have to provide A1, B0, C0, which makes now your first output, your output number 1 from the decoder, be low, activating this memory chip. Okay, so your beginning address of this memory chip would be, alright, 4 ones going here, then your B is 0, and your A is 1, and you have to provide again 13 zeros to get the data from the beginning address. So you would need this 0 to make hexadecimal conversion. So your beginning address would be F2, then 12 zeros. Here you are. This is your beginning address. Your ending address, you make these 13 zeros 13 ones. Again, this would be 1. You get the conversion of this final address as F3, then your 12, the other 12 ones. Alright, here you are, and so on. You can go over the 8 different combinations of these ABC through A13, A14, A15 of your address pins coming from your microprocessor. Okay, and here it shows the different address range of each of these 8 different memory chips. And this is the end of lecture 11. We'll meet you inshallah in lecture 12. Thank you.